Welcome everyone to today's IAMP One World Mathematical Physics seminar. This is the regular event hosted by IAMP, the International Association of Mathematical Physics. You can find more about this seminar and IAMP by visiting our webpage. Okay, so today it is our great pleasure to have Stefan Junk, who happens to be my colleague at Gakuen University, and he's going to tell us about the phase transition for the directed polymer model in higher dimensions. Stefan, the floor is yours.
Okay, yes, thank you very much. And first of all, thank you for the opportunity for me to give to you this talk today. And hopefully there is something interesting that I can tell you about this model, which is yeah. So I'm not 100% familiar how familiar people are with this directed polymer model. So I'm going to take it slow and give you introduction and motivation. And then the main point of this talk will be that I'll tell you about a new result with my co-author Hubert Lacoin, who is in IMPA in Brazil. And the result will be that a certain phase transition, well, two phase transitions in spatial dimensions larger or equal than 3 are actually one dimension. So the equality of two critical points. But before I do that, I have this slide here which introduces all of the participants in this model, and I have to apologize because okay, it's already introducing many things on the first slide, but unfortunately this model takes a bit of setup, and as I said, the motivation will come in a second. But broadly, the way to think about this model is that you have a random walk which is perturbed by a space-time random environment. So these are the two basic participants in the game. And the environment or disorder, so my background is from probability theory, so I tend to think of things as a random environment, but I think disorder is the term that is more common in maybe mathematical physics. It's given by, you take just an i.i.d. field of real random variables, with this law, this double bar p as its law, and you assume just the i.i.d. in its coordinates, and they are also very nice in the sense that they have all exponential moments. So if you take so this function lambda of beta, which will appear frequently, is just the log moment generating function. It's finite for all beta. So that's the first participant, that's the random environment. And then the second participant is a random walk, and the random walk is as simple as it can be. So it's just a simple random walk. So it starts in the origin, and then in each step you go to one of your 2D neighbors on the integer lattice in dimension D. And well, we have these two participants, and then we need some sort of interaction between them. And the interaction in this case is given by this path energy. And the path energy, so it's parameter, so you need to keep track of the time horizon, which is this small n here. And then what you do is you simply sum up what you saw in the environment. So if you have a walk of length n, then you just sum up the contributions that you see along the graph. So at each time coordinate, you take the contribution, the environments at that location. And then what is the central object here is this polymer measure, which is a perturbation of the simple random walk, where you give more weight to the paths that see positive parts of the environment than negative parts. More precisely, the weighing is done in an exponential fashion. So you take this path energy and you put it on top of an exponential. And then you also add an inverse temperature beta. So it's just a scaling factor that you can use to adjust the strength of the disorder. Okay, so that's the important part of this measure. And this is, okay, with respect to the density of simple random walk. And then, okay, then there is also in the exponential factor, there is here this deterministic normalizing factor, which is just minus n times the log moment generating function. This is mainly introduced for convenience. So it will be important that I have this factor here for later details. But for now, you can just observe that if you look at the normalizing constant, so this guy W down here, it has the same deterministic normalizing deterministic term in the exponential. So you could just cancel out these two terms, and it wouldn't influence the form of the polymer measure. And yes, so as is common in statistical physics, this normalizing constant here is called the partition function, and it will be one of the central objects in this talk. But for now, let me give you a simple illustration how the dynamics works. So this is one example of the kind of environment I would be interested in. It's just taking two values, which are in this picture here denoted by green and red dots. And they might mean, for example, -1 or +1. And then, okay, so I'm drawing the space on the horizontal axis and time in the vertical axis here. So a path is something like this graph here. And then the energy, for example, of the path I have drawn would be +2. Because if you sum up, well, hopefully I did it correctly, but there should be four red dots and six green dots. So the sum of the terms should be +2. And then you can consider another path, for example, this one x2, which is the same as the previous one, except you make a right turn where the other one, you make a right turn where the other one walks straight ahead. And then that one, for example, would have energy 0 because you have a negative one instead of the positive one. And okay, one maybe interesting path would also be this path x3, which is somehow well, you need to walk straight in a certain number of steps, but then what you can actually manage is to just see the good parts of the environment. So this path has the maximal possible amount of energy that any path can have up to time t. And okay, in this way, for any path of length 10, you can compute its energy. And then the point is that under the polymer measure, you choose a path at a probability which is proportional to beta times the energy and exponentially weighted. So what you can already guess from this is that if beta is small, then essentially how much the paths collect up to terminal time doesn't maybe matter too much because it's multiplied by a small constant. So approximately all paths would have equal probability, and therefore you expect some sort of behavior that is similar to the simple random walk. So the path tries to go in such a way that it has many choices for where it goes. And then if the beta is large, then you tend to more and more concentrate on the maximizing paths. So in this example, okay, I've shown you one maximizing paths. There might be others. But the important thing is that even if beta is very large, you always have some randomness. So it's not a strict maximization problem where you just try to find the maximal path up to time 10, but you give these paths a higher weight, but you consider all of them. Okay, and okay, maybe also a comment here is that from the physics point of view, like to call this quantity here an energy would be, well, okay, you would maybe prefer to have a minus sign in this in front of the beta, but since the environment, I make no assumptions on the sign of the environment, so I could just absorb the minus into the disorder and not write the minus all the time. So that's what I'm going to do. And okay, so I'm going to motivate introducing things in this way in a second, but let me just tell you that, okay, what we want to know about this model. We want to understand the long-term behavior of this measure, this polymer measure. So how does a typical realization of this polymer path look like? And we're going to find that there is an interesting phase transition where you go from a weak disorder regime where essentially you have the entropic contribution dominating, to a strong disorder regime, where essentially the path is doing some sort of optimization, and it's doing something quite different from simple random walk. Specifically, well, conjecturally, it is going to be super diffusive, so it's going to move further away from the origin than a simple random walk, and it's going to have a certain localization. So I'm going to explain in more detail what is the state of the art in this regime. And okay, so of course there is also some dimensional dependence here, which will also be there in a second. But before I do that, let me tell you, okay, so here is maybe a second picture here, which is okay. I just drew this on the iPad, but it's supposed to be a more long-term realization of this process. And I drew these two possible regimes. So note that I drew again some green and red dots, but you can imagine that all of the places where I'm not drawing any environment is just where the environment doesn't have any local preference to plus or minus, so it's just equal to its average. So in the weak disordered regime, the path will, okay, it still does some maybe mild optimization, but generally it more or less moves in the same way it always does. Whereas in this strong disorder regime, it somehow moves from areas which are kind of good, like these areas here, and these, and it tries to connect all of them and collect as much as possible. Now, if you just look at these two realizations, or these two pictures here, you might think that maybe these two paths don't look that difficult, that different. But one way to distinguish between this weak disorder and the strong disorder regime would be to sample a second realization of the polymer in the same disorder. And if you do that, you would maybe see something closer to what is drawn here. So the second realization would be this blue path. And the difference is now that in the weak disorder regime, the second path essentially moves like an independent simple random walk. So then it's going to have well, a small number of intersections, depending on the dimension, finitely many or maybe infinitely many. On the other hand, in the strong disorder regime, you expect that the second path, well, it's still in the same disorder, so it's trying to solve the same maximization problem. So it's going to follow more or less the same path as the first one. So the localization means that these two paths, they have a very large overlap because they visit the same areas of the environment. So that's the way to distinguish these two phases. Okay, so what I now want to do is to give you some motivation for why we study this model. So of course, you might think that this is an interesting thing or not, depending to study, but there are some, so I'm going to give you 3 reasons why this model deserves some study. And the first one is maybe the most trendy one in a sense. It's due to this KPZ universality. And so what we are trying to do here is to study, well, random interfaces. And these interfaces are in some way the result of growth process. So specifically, the interface is some sort of shape, which is, well, it's parameterized by some function h, which has a time and a space coordinate. And you have some evolution in time, and you have random fluctuations. And ideally, these kind of interfaces are supposed to model real-world physical situations. So one possible situation would be the accumulation of ice on the windshield, where the ice is somehow arriving according to some random process and then dropping down on the windshield and accumulating on the bottom here. And then you get this sort of interesting interface here. And then the second picture here shows something called the ballistic deposition model, which is a toy model for the first process here. And then there are other processes like the domain boundaries in magnets, or the burning boundary in some sort of paper, which are also expected to have this, well, that the interface is governed by these KPZ kind of fluctuations. And here there was this paper by these, Kardar-Parisi and Zhang, who introduced in already some time ago. They had this seminal paper where they introduced this equation here, the KPZ equation, and they suggested that a large class of random interfaces is governed by this dynamic. So it's a stochastic partial differential equation where you have you have a time derivative here, then you have a spatial Laplacian here. This term is, you take the gradient of your function, then the absolute value, and you square it, and then you also add a white noise. So that's going. So these are the random fluctuations. Now, I'm not going to explain why they propose to study this equation, but there is now considerable evidence that indeed this is has some claim to be the central object in this business. Instead, what I want to focus here on at the moment is that, first of all, that this equation is very ill-defined. And there are two problems. The first one is that it's a nonlinear PDE, so therefore it's inherently quite difficult to solve. And even worse, it's ill-posed in the sense that, okay, you have to take the gradient, but the roughness of the noise is such that you cannot expect that your function, that your solution is in any sense a good function. So your gradient will also just be a distribution, and then you need to take a square root of a distribution, and that we don't really know how to do. And of course, so by breakthrough works of Martin Heira and further works by other people, we now know how to do this in dimension 1, but in higher dimension, there is still, this is still quite unclear. And so how does this connect back to the model that I introduced before? Well, the first observation that you need to make is that there is a nice way to transform this equation by just taking a new function u, which is exponential of the previous function. And if you take the right constant on top of the exponential, then you end up with a second equation, which is quite nice and central to this business, which is called the stochastic heat equation. So essentially, if you take the right constant on the exponential, then the nonlinear terms disappear, and you end up with this second PDE, stochastic PDE, which is linear but still ill-posed. So now the problem is that you need to multiply your function, which is a distribution, with white noise, which is also a distribution. So you still cannot make sense of this, at least in higher dimensions. But now there is an interesting observation to be made, which is that you can actually write down, at least formally, what the solution to this equation would be. So they take this form of, okay, you take exponential of this term here, which is you take a time integral and then your Brownian motion, and you just integrate the noise that the Brownian motion sees along its path. And then there is also some deterministic normalization factor. And this hopefully should be somewhat familiar, because it's exactly the same as the model I introduced in discrete time. So the path energy is what the path sees along its trajectory, and then there's some deterministic normalizing factor here. So the partition function of the polymer model is a discrete space-time version of the solution to the stochastic heat equation. And therefore, you can use it by some approximation to discretize these equations. And okay, so one point of caution here is that even though you can write formally the solutions in this way, like both of these terms on top of the exponential are actually not well defined. So they are both infinities. So if you want to make sense of this connection, then there is more work to be done. But hopefully this does provide some motivation that this is a worthwhile thing to study. And the second motivation that I want to bring to you today is about the interfaces of the disordered Ising model. And in fact, this is the first occurrence of this model in the literature. So this was in 85 by these two people. And what they were doing is they looked at the Ising model with a random coupling constant. So there is some disorder, which in this case takes the form of a random field jx, y between neighboring sites, such that the partition function is perturbed by adding this random factor. So two spins x and y, how much they prefer to be alike or not alike depends on this random factor here. And then they made some simplifying assumptions. In particular, they studied the boundary condition where you have only pluses on the lower half and only minus on the top half. And what they're interested in is the shape of this interface that connects these two regimes. And the assumptions that they're making is, for example, that there are no overhangs, like for example in this part, and that there are no further minuses in the plus region and no minuses in and no pluses in the minus region. But under these simplifying assumptions, what they showed is that the law of this interface between the two faces, given the realization of the disorder, is very similar to, and they got an expression which is very similar to the polymer measure. And then even like very impressively, they predicted that the fluctuation of this interface, so if you take n as the side of your box and you're looking at what is the fluctuation that you can expect from this interface, they predict that these would be of order n to the 2/3. And 2/3 is actually one of the critical exponents in this KPZ business. So it's very impressive that they were already able to guess that from their numerics. And okay, one point of caution here is that this connection between the Ising model and the polymer model is only really there in dimension 1, because if you take the high dimensional Ising model, then the interface is going to be a d-dimensional object, some sort of surface, whereas in the polymer model, even in higher dimension, the polymers are always one-dimensional objects, like paths. And then I just want to briefly mention this third type of motivation. And the reason I want to mention it is because it's sort of an explanation why, for the name, like why do we call it the polymer model? And this motivation is from sort of a chemical perspective, where you try to model the shape of long molecule chains. And under some assumptions, you can assume that your molecule sort of starts from an initial point, and then in each step you add a new part to your molecule, and then there's some random angle between these, the first one and the previous one. So if there are no inhomogeneities, then your polymer is going to assume some sort of like curved, like a curled shape. But then you want to consider various situations. And for example, one interesting situation is where you have certain impurities, so indicated here by the green and the red points here. And maybe your polymer, it's attracted to the green parts and repelled by the red ones. So then maybe you might expect to see a situation like that one, where the polymer is sort of arranging itself in space to see as much of the green stuff as possible while avoiding the red parts. And then well, this you can do, but it's mathematically quite difficult because the path tends to visit the same areas over and over again, so you have some long-range correlations. So one sort of simplification that you might be interested in is to force the polymer to always involve in one space dimension. So you force it to be directed in, let's say, the horizontal direction, and therefore it cannot see the same impurity twice, so it always has to move forward. And then it's convenient to not think of it as a d-dimensional problem, but as a d-1 dimensional problem, and to relabel the directed coordinate as time, which is what we are doing. And yeah, so this is the reason why we call it the directed polymer model in random environment. And let me also give a warning here that the term polymer model, it's sort of an ill-defined term because it captures a wide variety of models. And so the general setup is always similar to what I did on the first slide. So you have some sort of random medium, or maybe not. So you can also do it in a deterministic setting. You have some sort of path energy. You have some sort of normalizing constant. And in the end, you always choose your paths with a probability that is proportional to exponential beta times the path energy. And then the normalizing constant will be the partition function. And then, of course, there is also this parameter beta, might be 0 or maybe even plus minus infinity. So this, of course, includes the setup of today's talk, where you have this sort of random space-time disorder that your polymer can pick up. There's also a close relative to this model, which is called the random pinning model, which is very similar, except that you only have this order at the origin. So your path can move around in space without collecting any rewards or punishment, and then it only collects the environment whenever it's back at the origin. So that's also a model that is quite intensively studied. And I also saw that in this seminar, there was recently a talk about the self-avoiding random walk, which you can also fit into this framework. For example, what you would have to do is you say the path energy is the number of intersections or the number of self-intersections that your path has, and then you take beta equal to minus infinity. So as soon as you have a single intersection, this exponential factor becomes 0, and otherwise it's just 1. And you can already see that these are very different models, and they are superficially described by the same setup. But well, the techniques that you need to analyze them and the kind of phenomena that you can expect for each of them, it's quite different. And therefore, I think that maybe, well, each of them, it's basically its own unique object, and you need to be careful about what kind of polymer model you have in mind. So are there any questions about the motivation and the general setup here? And, if not, I will maybe just very briefly say something about what happens in dimension 1 and 2, because I want to focus on the higher dimensional case. And okay, so I just point to this review paper by Nico Sigaras, which is quite recent and very nice. So if you want to know details about these regimes, then you should have a look there. But here I just want to say that in dimension 1, we have a pretty clear idea of what to expect. And the reason is that in that regime, we have integrable models. So models for which we can essentially compute everything that you would like to know. And the remaining challenge is to generalize it to non-integrable settings. And that challenge, well, that's certainly not easy. There are many open problems that are quite difficult, I think, but at least we have a general understanding of what to expect. And in dimension 2, things are becoming quite clear due to like very recent progress in, let's say, the last 5 years. Dimension 2 is the critical dimension. in the sense that if you want to use the directed polymer model to study KPZ and stochastic heat equation, then you need to renormalize in a certain way. And well, the dimension 2 is critical in the sense that the renormalization needs to be somewhat carefully chosen. And there is a number of works by these three authors which managed to construct a solution to the stochastic heat equation in dimension 2 using this directed polymer model, and in such a way that the limiting process, it's not the Edward-Wilkinson equation. So this would be, in a sense, the weak disorder case for the KPZ equation. So they constructed something which has which deserves to be called a solution to the stochastic heat equation. And here, well, there are still, again, many challenges. One of them would be to complete the program and get this to work for the KPZ equation. And then it would also be good to go beyond the parameter regime that was considered. But I'm not going to say more about this, except that, well, things are moving quite fast in dimension 2. And instead, what I want to do is I want to focus on dimension larger or equal than 3, where progress has been much slower and many more, like the basic shape of things is still much more open. And well, the main thing to know about higher dimensions for this model is that you have a phase transition. Now you go from this weak disorder to the strong disorder regime. I already showed some pictures of what that looked like. But of course, we need to mathematical definition of what these regimes actually are. And there is one natural way to define it. If you just look at the definition of the polymer measure, which is to consider just the denominator and to distinguish between denominator goes to 0 and denominator is bounded away from 0. So that you would certainly expect makes a difference for the behavior of the model, and in fact that is correct. And here it now becomes important that I have this normalization factor in the exponential, because this exponential factor is nice in the sense that it makes my partition function into a martingale. So as you reveal more and more of the environment, the partition function evolves as a martingale, and even better, it is a non-negative martingale. So we can, for free, we can be sure that the limit, that the denominator has a limit, which is this W infinity of beta. So it's a random object. And you can also say that there is a 0-1 law for the event of this denominator being 0. So either the denominator is 0 with full probability, or it's bounded away from 0 with full probability. And okay, that's already enough to define the weak and strong disorder regime. So the weak disorder regime is when the denominator is bounded away from 0, and the strong disorder regime is when it goes to 0. So in weak disorder, you expect that in a sense you can neglect the denominator because it's just a constant, and you can just focus on the numerator to analyze things. And in strong disorder, it's somehow more complicated because it becomes 0 divided by 0, so then it's more difficult to analyze. And we can also say that there is this critical parameter beta c, which separates the weak disorder from the strong disorder regime. So there is some monotonicity in beta, that as you increase beta, the limit becomes degenerate at one point. Now I'm going to complicate things slightly by saying by introducing a second phase transition, which is I think it might be the more natural way to define things from the physical point of view, where instead of looking just at the denominator, you look at the exponential rate of the denominator. So this is this quantity f of beta for the free energy, which is defined by just taking log of your denominator and normalizing by 1 over n, sending n to infinity. And this limit exists almost surely as well. And in fact, it's deterministic. And moreover, you can say that this quantity is always non-negative. So this is a simple consequence of Jensen's inequality. And moreover, as a function of beta, this function is continuous and decreasing. So if you draw a plot, then it looks somewhat like this. So it is constant up to a certain point, and then it goes away to minus infinity. And then the second way to define this phase transition is to say, okay, instead of just caring about when this denominator goes to 0, I care about the point where it starts to go to 0 exponentially fast, meaning the free energy is strictly negative. And in that way, you end up with a second critical value, beta c, with the overbar. And the regime beyond this value is what we call the very strong disorder regime.
Mhm.
So we have this
Stefan,
setup.
yeah.
Yes.
Can I ask two questions? So, yes, first of all, so you said there is a phase transition in dimension 3 or higher. So this means that
Yes.
you're sure you know that there's no phase transition in 1 or 2 dimensions.
Yes. This I will explain in more detail on the
Oh,
on the
okay,
next slide.
okay.
For now,
Yes.
these critical values are allowed to be 0 or plus infinity.
Mhm.
So I'm
Okay.
leaving it open. Yes.
Okay. And the second question is that probably this is more complicated, but you said that this measure P itself does not depend on this normalization with n lambda beta. You even
Yes.
said that this n lambda beta is more or less artificial. But now these criteria for phase transition essentially depends on this normalization
Yes.
factor. Mhm.
Yes. So
Hmm.
you want to introduce this factor, which you say it's arbitrary, that's correct. But if you want
Hmm.
your denominator to converge, then you have to take that factor.
Hmm.
And the convergence for the denominator is sort of the natural thing you want
Mhm.
to have.
Anyway, and it has something to do with the property of this measure. Is that
Yes.
correct? Yeah,
Okay. So
probably it will be.
so e to the power
Mm,
of n times lambda beta
mm,
is just the expectation of the unnormalized guy.
mm-hmm,
So you're just
mm-hmm,
dividing by the expectation, basically.
mm-hmm. Okay, thank you.
Okay, so we have these two phase transitions, but as just mentioned, we need to talk about whether or not these are actually trivial or not. So the definition here I just replicated from the previous slide. But then in dimension 1 and 2, indeed turns out that there is no phase transition. So both of these critical values are known to be 0 by work, well, first by these two authors who first showed it for the strong disorder, and then by Hubert Lacoin, who proved that also the critical value for very strong disorder, they are both 0, meaning that as soon as you take strictly positive beta, you are in the strong disorder regime. So there is no weak disorder regime in low space dimensions. On the other hand, in dimension larger or equal than 3, both of these values are known to be strictly positive. And this is actually, so the proof that this is the case is done by Balthausen already quite some time ago. And he was in fact the one who introduced this normalizing factor and introduced the idea of using martingale techniques to this model. And I should say that also in dimension larger or equal to than 3, it is possible that the critical value is positive infinity. So you only have a weak disorder regime. But this is not very interesting, and you can ensure that there is a real phase transition under some easy conditions, which are not so interesting. So I didn't do it. And maybe it's enlightening to also present this result that me and Hubert Lacoin had this year. So it's a generalization of this model where instead of taking simple random walk, you just define it by x, any kind of random walk supported on the integer lattice. So no assumptions on the random walk. And then we showed that in this setting, it is true that you have this phase transition if and only if the difference between two independent copies of your random walk is transient. So it's about the transience of that of the underlying random walk, which is the important thing. Which for simple random walk, of course, it's dimension 3 and larger. Okay, so as I said, we're focusing on dimension 3 and larger. And I just want to briefly tell you what is known about this localization behavior. And again, there are two notions of localizations. The first is what I'm calling endpoint localization, which is that in the strongest order regime, it is known that if you take two copies of your polymer in the same environment, so independent but affected by the same disorder, then they have a positive probability of being at the same endpoint infinitely often. So you take the limit superior of the probability that they agree at the endpoint, and this is strictly positive almost surely. So probably it's easier to understand by picture. So now the black and the blue path are two independent realization of the polymer in the strongest order regime. So they're both very much trying to optimize their paths and picking up the environment as much as possible. And then if you have something nice around the terminal time, well, then it's a quite good idea, or it's quite likely that they end up in the same endpoint. And the statement is that this happens with positive probability infinitely often. And a second notion, much more recent, which goes towards quantifying this picture of full path localization that I drew in the beginning of this talk. So, okay, the statement here is kind of complicated, but let me just point out the important thing that so there is some value large n, such that if the time n is large enough, you can find certain paths pi1 to pi large n, so random variables depending on the environment, such that the following holds. So you count how many time steps your polymer intersects or is exactly the same at exactly the same location as the path pi I. You sum up these times up to n, and you want the fraction of the time that this is true to be larger than delta, and this is supposed to happen for some I. So this event happens with large probability. So let me just show you the picture, which is probably more helpful. So now the path is pi 1, 2, 3, and 4, maybe these 4 black paths here, which are sort of possible trajectories through the environment that are quite good for the polymer to take. And what they're saying is that the polymer is going to pick one of these paths and follow it at least a positive proportion of the time. So that's the statement that they're considering. And the thing that I want to point out here is that there are some assumptions here. First of all, they only prove it for the Gaussian environment. And then they also prove it only for such beta, such that the free energy is differentiable and the derivative is strictly negative. And in particular, what this means is that this result requires really very strong disorder. So this endpoint localization requires strong disorder, but the full path localization, the more complicated but more mathematically satisfying result requires very strong disorder and some additional conditions. So that's in a sense the explanations why these two regimes are both relevant and have been studied in the past. And now the good news is that we proved that actually these two regimes are the same. So this was first conjectured by Carmona and Hu. So in the paper where they also proved the statement about endpoint overlap, they conjectured that in fact these two critical exponents should be equal in any dimension. And then this conjecture was already resolved in the lower space dimension by just computing explicitly that these critical values are both equal to 0, and therefore, of course, they agree. And so this was, if you remember, this was completed in 2010, so quite soon after the conjecture was formulated. And now in 2 works, this year and last year, we were able to verify this in higher dimension as well. So we show that these 2 critical exponents are equal. And let me also say at this point, maybe I should have said this earlier, that the explicit value of beta c, you cannot compute it. So there's no closed form for what it should be. So we prove it without identifying the critical value. So let me give you some more details about the main result. So what we actually show is the following. So you assume that you are in a dimension larger or equal than 3, and also you assume strongest order. And that immediately implies that the free energy has to be strictly negative at that point. So as soon as your martingale converges to 0, it has to do so exponentially fast, is what we proved. And the first corollary of this is, of course, that these 2 critical exponents have to agree. So that's for free, essentially, from this result. But then a second observation is that actually you can now say something about what happens at criticality. So if you look carefully at the definition of the critical exponent, I just said that, okay, up to beta critical, we have weak disorder. Beyond beta critical, we have strong disorder. I didn't say what happens at criticality because it's only known thanks to our result. And specifically, what we show is that at criticality, we have weak disorder. And the argument is actually quite quick. It uses the fact that the free energy is a continuous function of beta. And because it's a continuous function, it has to equal 0 even at the critical point, because it has to equal 0 up to that point. And if it equals the critical point, then by our result, it means you cannot have strong disorder at that point. So therefore, you must have weak disorder, because you must have one or the other. So that's the first thing so as far as I know, there wasn't really a conjecture about which kind of regime you should have at criticality. So I was quite happy that we could resolve this. And in fact, we can say slightly more using some other results that maybe due to time reason I will not explain. But what we can say is that something about the critical integrability of this process at criticality. So specifically, this process, it's a martingale. So therefore, of course, it has to be L1 bounded. But we show that actually it is, well, the critical value of P such that the process is LP bounded. It is this. It's 1 plus 2 over D. And well, this value we identified by using previous work on the weak disorder regime, which I will maybe skip. Except the maybe interesting thing to point out is that the critical integrability, since D is larger or equal than 3, this value is actually smaller than 2, meaning that you cannot use L2 techniques up to the critical point. So this was already known, but so for a while there was a conjecture that the critical point was equal to just the L2 critical point. So the point where this martingale fails to be L2 bounded, but this turned out to be false. Instead, well, it's this strange fractional exponent here. And okay, I don't have time to give an intuition for why this value appears, but hopefully we can use this information to say more about the model at criticality and beyond. And okay, so I was planning to say something about the ingredients of the proof, but maybe I will just so I will just do the first slide I have prepared for this. And so the first thing we do is that we use a fractional moment technique, where instead of looking at, well, natural thing to do would be to look at the log of the partition function, but the log is kind of a difficult object to consider. So instead, what we do is we study the square root of the partition function. And well, the reason why this is a good thing to do is that remember that the process, it's a martingale, meaning that its expectation is always constant. On the other hand, we know, or we're trying to prove that the process converges to zero even exponentially fast. So the only way that it can have expectation 1 is if there is some event where the martingale takes a very large value with very small probability. And that's sort of supporting the expectation, so the first moment. And if you take the square root, then you sort of get rid of this contribution from the large values, because now suddenly what you gain from that is much smaller, and you got rid of it, and only the dominant terms remain. So that's morally the reason why fractional moments are interesting. And then we proved this lemma here, which, well, we proved it, but it was definitely already known. So this is a general thing in this business. That in fact, so we want to show that this guy converges to zero exponentially fast, and you can make your life much easier, because it's enough actually to just show polynomial decay. So as soon as you have this polynomial upper bound for some n, you have an upper bound on the free energy, and therefore you know that the free energy is strictly negative. But of course, you still need to establish this bound, which, okay, it's polynomial, but still you need to do some work. And the way we bound this fractional moment is by a change of measure argument, where we define a new measure p n tilde by just taking the partition function itself as the density. So the probability of an event A under this tilted measure, it's the expectation of Wn beta times the indicator function. And then the way to use this is that we can bound the fractional moment by, well, the probability of an event A under the original measure and the probability of the complement under the tilted measure. And this is true for any measurable event A. So what you need to do in order to get an upper bound on the fractional moment is to find a good event A to plug in the right-hand side. So an event A for which both of these terms are small. And the intuition for that is that we expect that our guy, so Wn beta, is small, in fact, exponentially small with very high probability. So in this change of measure here, it's highly singular. And well, if you remember the definition of singularity, it's essentially, well, this is essentially a way to quantify how singular the two measures are. And specifically, what you need to do is to find an event which distinguishes these two measures. So these two measures are singular, and so in a sense they have disjoint support, and you need to find an event which captures that. And the way to, well, okay, this you can always do, but of course it's useless unless you have a good control on this tilted measure, which in this case we do. So this is also not new. So this is done due to work by Matthias Birkner already quite some time ago. And he showed that this change of measure is nice in the sense that we can give an easy construction for how the tilted environment looks like. So namely, you need three ingredients. You need a copy of your original environment. You need this environment omega hat, which is the size bias of the original environment. So okay, I'm not defining the size bias, but the important thing is just that the W hat is stochastically larger than the original environment. So if, for example, if your environment is Gaussian with a certain mean, then omega hat would be a Gaussian with a larger mean. So it increases, in a sense, the values of W, of omega. And then the third ingredient is just a copy of the original simple random walk. And then what you do to get an environment under the tilted measure is you take the environment, the original environment outside of the spine, and on the spine, you take the size biased one. So you make the environment larger along the spine. And then, okay, so this is the last thing that I'm going to say. But the intuition is that the event A that you're going to choose is something that captures that the environment is larger along the spine. So if you look at the original environment and the new one, the difference is that there is this spine where the environment is slightly larger, and you define an event A which captures that. So I had included some more details here, but I think I want to finish here. So thank you for your attention.
Well, thank you very much, Stefan, for the beautiful presentation of the beautiful new results. Okay, so now it's time for questions and comments. If you have any question or comment, just please unmute yourself and ask.
I see there are some.
Well, they are just
questions
clapping hands. Yeah. But Ryoki,
Okay.
yeah.
Maybe can I
Also-
ask one question?
Oh, yes, please. Yeah.
So you could also integrate out the randomness, and you would get the interacting random walk with like on-site interactions. Am I
So,
wrong?
okay, it depends. You want to take an expectation of this measure here?
Yes.
Yes. So I think that doesn't change anything. So you still have to look at the quenched object and then analyze it. So like if you integrate out the environment in the partition function, it's just constant. If you try to average over the polymer measure, because there's this denominator here, it doesn't simplify things, I think.
Right. So the quench measure would be a measure with some kind of potential, which depends on how many times you go at the same site. But it's true, it would be a different measure because
yes. Well,
sorry,
you can only
you have a quench, and what I suggest is more like the annealed measure, I guess.
Yes, but even under the quench measure, you can only pick up a contribution once because you're directed.
Yes. So that's a difference from the standard business of random
Yes.
walks. Yes.
You're not allowed to go back and just visit
Right,
the same
yeah,
location.
Yeah,
So
sure.
yeah, I think if you forget about the denominator here and just integrate out the numerator here, it will just become the simple random walk again. So you will completely lose the randomness.
Right. Hey,
Thank you. Yeah.
any other questions? Comments? So yeah, can I ask one? So you showed that at the critical point, beta 3, this W is strictly positive.
Yes.
So this means that W sort of shows a jump
Yes.
from 0 to So was it
Yes.
expected or conjectured, or was it totally new finding?
So okay, I was definitely surprised. So what is known is that if you look at what you can do is look at the W infinity as a function of beta. And it is known to be an analytic function, well, at least until close to beta critical, and probably it's analytic up to beta critical. So it only has this one jump at the critical point.
Okay.
and then whether or not this behavior was expected. So we can find different predictions in the literature. So what people have been doing before is to look, for example, at the model on the tree. So instead of integer lattice, you have a tree, and then each step you have to go deeper into the tree, so away from the root. And that's kind of a nice model because you can actually compute everything. So you can compute the critical point, for example, and it actually has a different behavior. So at that point, you have strong disorder, and the phase transition is more continuous in this sense.
Oh, yes. Okay. So, yes, this tree thing is sort of infinite dimension approximation, but yours infinite dimension showed something different.
Yes.
That's interesting.
And then there was also some work on what is it called? So some sort of fractional approximation of the integer lattice that you can use to, like, okay, I think it's kind of used to approximate the integer lattice while still having some more structure. Sorry, I just forgot how it's called. It's like
hierarchical model or what?
yes.
Okay.
Sorry, yes. On the hierarchical lattice, you can actually have the same behavior, that you have weak disorder at criticality. And it's actually quite easy to show it. So there's some recursive structure due to the fractional nature, and then it's for free, sort of. So I would say that it was quite unclear what happens at criticality.
And as a physicist, I'm interested in, does it suggest anything interesting? What does this discontinuity means? Sorry, this is just a physics curiosity.
What does it mean? Yes. So in a sense, it is good news because like what we ultimately want to do is we want to understand the strong disorder regime, and one way to do that is by some sort of perturbative analysis. So you start from the critical value, and then you go into the strong disorder regime. And the fact that you have weak disorder at least tells you that you have something well behaved from which you can do your perturbative analysis. Because, so I didn't say it, but in the weak disorder regime, we actually have a central limit theorem for this polymer measure. And that includes the critical case itself. So at criticality, we now know that the polymer part has a Brownian motion as its scaling limit.
Yes.
And therefore, it's quite a good point in a sense to do any perturbative analysis from. But of course, still many details to be done.
Oh yes. That was partly the question that I wanted to ask, but very good. So any other questions or comments?
Hello, and this is Rocky. I have a technical question. So your results so far is about discrete space-time model, but there are space-time continuous model like Brownian polymer in whatever noise, Poisson point process or Gaussian noise. And do you have an expectation that your result can be extended to a continuous model?
So, okay, we actually did prove the main technical step for the result in a space discrete but time continuous model. So you take a Brownian disorder at the points, and yeah, I would certainly think that you can do it for Brownian polymer as well, modulo some technical modifications.
Yeah, because in the last step you use this size biasing, and
yes,
I'm not sure how it goes for continuous model.
Yes, but okay, there are alternatives to the size biasing. So I think it's not obvious, but yeah, so there is some work to be done. But I would certainly expect that it's possible.
Very good. Thank you.
Very good. Any other questions?
Okay, I'll ask one.
So, all right. Yeah, please.
Yeah, so Stefan, a very nice talk. Thank you. I wanted to just ask for a comment on what happens when you replace the simple random walk with a general walk. It seems you have results in this setting. Are there complications that are serious with proofs? Especially when the walk changes the critical dimension.
So we have a result which is quite general in the sense that we only require some tail condition on the increment of the random walk. So as soon as your random walk has any sort of moment, so as soon as it has a finite epsilon moment, everything goes through. And then we actually have a counterexample that if your random walk doesn't have any moments, so the absolute value of the first time step, then you can. It is possible that you have strongest order, but not very strongest order for all positive beta.
I see. Okay, interesting. Thank you.
Okay, any other questions? If not, we are already in Wednesday. So let's thank Stefan again. Thank you.
Yes, thank you for having me.